Hello everybody. So in this video we're going to start the derivation of the pressure at a point, which is the pressure at a point under static fluid. So this is a very important thing because there are a lot of things that we are going to do until the end of this chapter that relate to this point, is how the pressure affects a specific point in a static fluid, or how the static fluid exerts pressures on objects. To be able to do this, since we are interested in pressure at a point, we are going to do this derivation on a differential element, as we said before, a differential element under or in a static fluid. This differential element will be a triangular prism in shape. It has triangle dimensions delta x and delta z, and the height of the prism is delta y. This length is going to be L. Towards the end of this video, I'm going to discuss, or at the end of the derivation, I'm going to discuss why or explain why we chose this shape specifically, because there is a good reason of choosing this shape other than other simple shapes like the cube or cuboid, for example. So this is there is a reason for picking this shape specifically. But what we're going to do here is a very simple derivation. This is a very simple derivation. This is the prism. These are the dimensions delta x, delta y, and delta z, and this is the length L. And all what we are going to do is just apply Newton's law, which states that a body at rest is exposed to or the sum forces on a body at rest is zero. So this is simply what we're going to do. And we already agreed before that in static fluids, the type of forces that we are going to consider are only the normal forces, not the tangential forces, which are results of the normal force, which is the pressure, rather than the shear force, which is not included in the static fluids. So there are no shear forces. The only forces that we are going to include are the normal forces, which are the pressure forces. So we know that the normal forces are perpendicular to the surfaces. So we have here 5 surfaces in this shape. We have this rectangle, this rectangle, this rectangle, and the 2 triangles, one on this side and one on the other side. So we are only going to include the forces on the 3 rectangles, not on the 2 triangles, for a reason that I'll mention later. To make it easy, and as I said, it's going to be sigma f in x direction, and y and z direction are going to be zeros because it's in state of rest. In each direction we have to, or for each face we have to see what is the force, and the force is the result of the pressure. So we have here a pressure P1 acts on this surface that has an area of delta y, delta z. We have pressure P2 that acts on this surface, which has an area of delta x and delta y, and we have P3, which is acting on a surface with area delta y L. And since we are interested in the forces in x direction, in y direction, and z direction, so we have to get the components of this P3 in x and z direction. So this is the z direction, this is the y direction, so we'll have 2 components. This is angle theta, which is going to be the same as this angle theta here. So we can get the component in the vertical direction, which is P3 cosine theta, and in the horizontal direction, which is P3 sine theta. And now we don't need P3 anymore. We have already the components of P3 in the vertical and horizontal direction. So for the let's take for the x direction, the force we have here is P1 times this area, which is delta y delta z. And we have on the other direction P3 sine theta times the area, which is delta y times L. Okay, so this is P1 delta y delta z minus P3 delta y L sine theta. We can cancel delta y in the two terms, so it's going to be P1 delta z minus P3 L sine theta is equal to 0. For z direction, we have P2 times delta y delta x, which is this first term here, minus the force acting on the other direction, which is P3 cosine theta times L times delta y, which is P3 cosine theta times delta y times L. And we have the gravitational force as well, which is mg. Okay, so it's acting in this direction downward, which is the negative direction, so it's mg. And the mass is the density times the volume. The volume is the volume of this triangle times the length or the height, which is delta y. So it's half delta z delta x times delta y. So this is the mass, of course, times rho. This is the mass. And then we can put everything together. So it's P2 times delta x delta y minus P3 times delta y L cosine theta minus half, which is m rho delta x delta y delta z times g. Again, we can cancel delta y in the three terms, and the equation is, as you see here, P2 delta x minus P3 L cosine theta minus half rho g delta x delta z equals 0. Now we want to simplify the equations more. So we know that these are the two equations that we have, and we know that we can get relation between L delta x delta z through the angle theta. So from the geometry, we know that sine theta is delta z over L. So delta z is L times sine theta, and we know that cosine theta is delta x over L. So delta x is L cosine theta. We have here L sine theta, and we have here L cosine theta. So we can replace this by delta z and replace this by delta x. So by substitution, we will find that P1 delta z minus P3 delta z equals 0, which means that P1 equals P3. The same for the z direction. So you have P2 delta x minus P3 delta x, which is this, minus rho g delta x delta z equals 0. We can cancel delta x in the three terms, and the equation is going to be P2 minus P3 minus half rho g delta z equals 0. Remember that this element, or this element that we took from the fluid, is a differential element, which means that it's very, 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 very small, and the value of delta z is very small compared to the pressures. We don't cancel it in general, but we cancel it here because this is a very, very tiny dimension compared to the pressures, which will make this term very negligible compared to P2 and P3. So we can ignore this term, and we will end up with P2 equals P3. So from these two equations that we have here, we know that P1 equals P3 and P2 equals P3. So P1 equals P2 equals P3. Okay. Now this is a good thing to notice here, and to know why we chose this shape to make the derivation. The reason is, if we use any cubic shape or any other shape, the derivation will end up with P1 is equal to the pressure in the other direction, P2 is equal to the pressure in the other direction, and we don't have any relations between P1 or the pressures in the horizontal and the vertical directions. But when we use this inclined surface, we have the same pressure here. It's a common pressure in the horizontal equation and in the vertical equation. And now we can get a relation between P1, P3 and P2 and P3, so we can get a relation between all the pressures in the different directions. The other thing is that this is a general equation that we can use for any angle theta. So it's not only valid for vertical surfaces if it's a cube or a cuboid, but it's valid for any direction. It doesn't have to be in a perfectly horizontal surface or a perfectly vertical surface. It can be for any inclined surface or even a curved surface. So this makes this derivation more general and valid for any case. Okay, and now we can get something useful out of this. From the derivation, we find that the pressures in all directions are equal. which means that the pressure at a point in a fluid has the same magnitude in all directions. This is a very, very important thing. So for any point under specific or under a fluid, it's exposed to pressure in all directions with the same magnitude. In all directions with the same magnitude, which is a very, very important thing. Okay, so it doesn't have a specific magnitude, it's a scalar quantity. Pressure is a scalar quantity, it doesn't have a specific direction. It has a magnitude that is affecting the point in all directions. Okay, so from the right and from the left, from the top, from the bottom, from any angle, the point is exposed to the same pressure in all directions. And this is valid for static fluid, and it's also valid for dynamic fluids. And this is something we will see later, that for dynamic fluids we can use the same concept, that the pressure is affecting the fluid in all directions. So it's not a scalar quantity, it's not a vector quantity, it's a scalar quantity. Of course, based on this pressure, we can get a vector quantity, which is the force. And this depends on the surface that the pressure is applied to. But this pressure itself is a scalar quantity. Now, why is this important? This information important? This is very important because a lot of things depend on this pressure. So if the pressure has a direction, or if it had a direction, then a lot of things would be different. So knowing that the pressure has no direction or no specific direction, and it applies affects the surfaces on all direction, has a very important impact on designing the bases and supports of platforms that are operating under the surface of water, in oceans to extract, or in seas to extract crude oil and natural gas from the wells under the sea surface. So the design of these supports is very important. It's very, very important. So you need to know, or we need to know, how much force is acting and in which direction. So knowing that the pressure is affecting in the point in all directions affects the design of the bases of the supports of the platforms. Besides, for another example, for example, in the pipelines or the cables that are used to transfer the internet or connect the internet from a continent to another, these are buried in very, very deep distances in the oceans. So they have to be designed in a way to withstand the forces acting on them, and these forces are based on the pressure, and they have direction based on the direction, or whether the pressure has direction or not. So the design of these things are very, very dependent on this information that we know, which is that the pressure has no specific direction and it affects everything in the same way, or a point in the same way from all directions. So this is a very, very important piece of information. Now, knowing this information is very useful, but then there is another question that will come up now, which is how much pressure is the static fluid acting on the point under the surface, or in the static fluid. And this is a very important question, and we are going to go through the answer in the next video, inshallah. So I'll see you then. Goodbye.